Water recovery, water pollution control, we need to remove a certain amount of bugs out of the system every day to keep the bugs in balance. And that's important process control parameter when operating a water pollution control facility, is to remove a correct amount of bugs out of the system. Otherwise, these bugs will rise in the secondary clarifier, and we don't want that to happen. So here you can see a secondary clarifier. The scum on top is a filamentous organism. This is it's May 2017 right now, where the water temperature is getting warmer and the environment for the bugs start to change, and we'll get a little bit of nocardia growth that you can see. So this secondary clarifier is bigger in diameter than the primary clarifiers, and here the activated sludge settles to the bottom, and the clarified, what we call effluent, rises to the top and goes over the V-notch weirs, which is now called secondary effluent. Here's the water going out of the plant onto the chlorine contact tanks for disinfection of E. coli and any pathogenic microorganisms. And in the middle ring there is the actual activated sludge coming out of the aeration tanks and into this tank where they settle. Again, we have a skimming mechanism with brushes, and the brushes clean the launders, which is the effluent channel of the secondary clarifier, skims it into this trough, and that's again pumped to our sludge removal system. The secondary effluent then flows to these chlorine contact tanks. We have two. This is chlorine contact tank 1, and that over there is chlorine contact tank number 2. That was part of our upgrade, which included adding a chlorine contact tank, one secondary clarifier, an aeration tank, a primary clarifier, and the blower sludge building. $28 million project back in 2002. So we're coming up on 15 years ago already. So here the water flows out of the secondary clarifiers into these chlorine contact tanks. So down in this influent well, we're dosing sodium hypochlorite, 15%, into the water, and there's a mixer submerged in the water, thoroughly mixing the chlorine in contact with the water here, and we're disinfecting, removing pathogenic organisms. And these chlorine contact tanks are designed for a detention time of a minimum 30 minutes. So the chlorine efficiently disinfects the water, removes a certain amount of E. coli, and we measure E. coli and do a laboratory test 3 times a week. Here at the end of the tank are scum troughs. Again, we'll operate these once a day and remove the scum from the top that rises to the top, goes to the sludge storage tanks. And here's the outlet side of the chlorine contact tanks, little waterfall. And here at this point, right here, is where we have to dechlorinate our water, because we cannot send chlorine concentrated water to the river, because chlorine will chew up the oxygen in the river, deplete the oxygen, and kill all the aquatic life, fish, plants, and we don't want that. So what we do is dose sodium bisulfite to dechlorinate the water before it goes in the river. Here is the other chlorine contact tank, and the outfall from this chlorine contact tank flows through this channel that we were just looking at. It'll flow, it comes in on that side, flows through and gets dechlorinated, and then it flows to our outfall chamber over here. I will show you the other chlorine contact tank. Here's the waterfall from chlorine contact tank number 2. Flowing through the outlet channel of chlorine contact tank number 1. Again, there's a scum removal device, scum troughs. We'll go to the controller here, the output, and it's flowing 2.8 million gallons per day. So as you can see, the influent was around 4 something million gallons per day, and we're around 3 million gallons per day. So what we're doing is removing about 1 million gallons of water per day on average, which is the fluid containing all the grease, scum, sludge, activated sludge, and then we thicken it and dewater it. But here's the ultrasonic level transducer measuring the outfall level, and here's the water leaving the facility after final. So the water at this point has gone through the bar racks. It's been through the aerated grit chambers. It's gone through the primary clarifiers, through the aeration tanks, settability in the secondary clarifiers, chlorinated in the chlorine contact tanks, dechlorinated by sodium bisulfite, and here's our final product flowing out to the river, clean water. This water right here is good quality effluent, less than 10 milligrams per liter total suspended solids, biochemical oxygen demand lower than 10 milligrams per liter, low levels of phosphorus, 0.3 milligrams per liter total phosphorus, 3 milligrams per liter or less of ammonia, and various metals, and low levels of E. coli. A flood condition, we have to pump it into the river. And there's the control panel and electrical disconnects, and this is the back end of the plant. And then down that path through the fence there, underground pipe, is where the final effluent is discharged to the Westfield River. Here is our sodium aluminate tank. This is a chemical to help us remove phosphorus. It's a precipitates the phosphorus. We used to dose $250,000 worth of it. Now we dose $60,000 worth annually. Almost a $200,000 savings. And here's our storage tent where we have our Kubota tractor. Very helpful tool. Mower deck, snow blower, bucket. And here we have our trailer mounted trash pump that's got the capacity to pump 1,300 gallons per minute. We use this at pump stations. It's a emergency fail-safe where we can bypass a pump station if the generator fails to run. And we can pump out our chlorine contact tanks and secondary clarifiers with this machine. It's been very useful. We've had it for a little. Okay, we're in the blower sludge building. This is the loading dock area at the rear of the building. Storage of air filters, liquid polymer. Here's our sodium hypochlorite room, storage tanks. 15% sodium hypochlorite, bleach, and various pumps to pump the chlorine to different locations of the facility. Gravity belt thickeners. These machines here thicken up our activated sludge that we waste out of the system. So in this inlet box, the activated sludge is mixed with a polymer which coagulates and separates the water from the sludge. The water gravity flows through this belt, and the sludge stays on the belt, goes over these plows. So when the plow is down, The sludge goes over these plows and helps separate the water. And off the back side, the thickened waste activated sludge then dumps into the sludge storage tank. So we go from about 0.5% solid solution of bugs, waste activated sludge. On a good day, 6.5% solids concentration off the discharge end of this machine. And there are the polymer pumps and the tote, 250-gallon tote of liquid polymer that's dosed at a specific concentration to the inlet piping here, and then it's mixed in this influent box and the machine is run. We can process approximately 180,000 gallons per day of waste activated sludge. Many treatment plants in the area don't even have that flow coming through their headworks. Here is the sodium hydroxide, other known as caustic, solution storage tank, 25%. And here are the pumps, peristaltic, positive displacement pumps that are dosing the sodium hydroxide to the aeration tanks, to the bugs. When the bugs consume the organic material and oxygen, they deplete the alkalinity. And to replenish the alkalinity, we need to dose sodium hydroxide at specific rates. Here we are in the generator room. Here's our 900 kilowatt CAT generator. In emergency situations where we lose city power, this generator will power the entire facility, and we exercise this once per week, have it well maintained. And in the summer, during thunderstorms, ice storms, snowstorms, we lose power frequently. So this machine, this generator, diesel powered generator, is crucial to keeping our treatment process functioning.